how do you perfectly balance a completely flat, straight line on the exact edge of a continuous curve? It is a challenge of precision, where the line makes contact at one infinitely small point. Let's start with the basic components of a geometric plane. We have a circle and a single radius segment drawn exactly from its center out to the perimeter. If we drop a straight line across this plane, it naturally forms a secant. A secant is simply a line that intersects a circle at two distinct separate points. Watch what happens as we pivot that intersecting line outward. The two intersection points get closer and closer together until they merge. The line now touches the outer perimeter exactly once. This is a tangent. Geometry gives us a strict rule for this relationship, known as Theorem 6.4.1. This line is only a verified tangent if and only if it is exactly perpendicular to the radius at the exact point of contact. That 90-degree lock is the absolute mathematical proof. Without it, the line is just a visual estimation, hovering somewhere near the edge. This creates a core tension. In formal geometry, we cannot rely on visual estimation. We have to strictly construct this perfect 90-degree alignment manually, using nothing but a compass and a straight edge. Creating a tangent is a rigorous engineering problem. It requires precise construction of a flawless right angle to anchor the line to the curve. Let's look at the first practical challenge, drawing that perfect tangent when we already have a specific starting point sitting exactly on the circle's edge. This process is formally known as construction 8. We start with two established parameters, the center of the circle, labeled P, and our target point on the perimeter, labeled X. The first step in our strategy is to draw the radius from P to our target point X, and then extend that segment straight outward beyond the circle to form a longer line. Next, we use point X as our anchor. By placing the point of a compass at X, we strike two equidistant arcs across our extended line. This creates two symmetrical reference points, labeled Y and Z, on either side of X. Now, we expand the compass radius. From our new reference points Y and Z, we draw two intersecting arcs further out. The spot where they crossing becomes point W. Drawing a straight line from W down through X gives us our tangent line. By forcing a perpendicular bisector precisely at the perimeter, we have satisfied Theorem 6.4.1. This mathematical construction guarantees a flawless tangent. What happens if we apply this exact tangent construction to four sequential points around a single circle? Points A, B, C, and D. The four tangent lines intersect to form a bounding quadrilateral around the outside of the circle. Let's impose a specific condition on this geometric shape. We will position points A, B, C, and D so that all four of the arcs between them are perfectly equal in measure. This symmetry yields a specific geometric result. The tangents intersect each other at 90-degree angles, creating a perfect bounding square. If we adjust the points so they create symmetrical pairs of arcs, where the top and bottom arcs match and the side arcs match, but not all four are equal, the shape reacts. The 90-degree corners vanish, and the square skews into a rhombus. The shape of the external bounding geometry is entirely dictated by the internal division of the circle's arcs.
Now we face a much more complex mathematical challenge, detailed in Construction 9, engineering a tangent line that originates from an arbitrary point floating completely outside the circle. Here is the starting scenario. We have a primary circle with its center at Q and an external point floating in space, labeled E. We connect them with a single dashed line segment. The first step is finding the exact center of that connecting line. We construct a perpendicular bisector to drop straight down onto line EQ, giving us a distinct midpoint, labeled M. Here is the trick. We use that midpoint M as an anchor to draw a secondary, larger circle. This new circle is sized to pass exactly through our starting points, E and Q. Look at where the two circles overlap. These two intersection points, labeled T and V, are exactly where our mathematically perfect tangents will touch the primary circle. To complete the construction, we draw solid straight lines from our external point E straight to these new intersection points. We know we need a perpendicular angle for a true tangent, so why does drawing a second circle guarantee a perfect 90-degree alignment at point T? The proof is hidden in the geometry of the larger circle. If we draw a triangle connecting E, T, and Q, we can apply Thales' theorem. Faley's theorem formally states that any angle inscribed inside a perfect semicircle is exactly 90 degrees. Because line EQ is the diameter of the large circle, the angle at T sits inside a semicircle, making it a perfect right angle. The secondary circle was a geometric tool used to force a 90-degree angle, satisfying theorem 6.4.1 and proving that the line is a true tangent. Let's pivot our focus away from the external edges and look inside. There are strict proportional rules that govern the interior of a circle just as rigidly as the tangents on the outside. A central angle is formed by two radii extending from the center. Where these radii hit the edge, they intercept a section of the perimeter, known as an arc. The rule here, a larger central angle always corresponds to a larger intercepted arc. The converse of this rule is mathematically guaranteed. If you measure a larger arc on the perimeter, you are certain to find a larger central angle anchoring it. The internal angles of a circle act as an unbreakable map for the distances along its perimeter. This internal mapping applies to chords as well. A chord is a straight line segment whose endpoints both lie anywhere on the circle. The challenge is understanding how their lengths relate to their position. If we place two chords of visibly different lengths inside the exact same circle, we can see they sit at different depths. To accurately measure a chord's placement, we drop a perpendicular line directly from the center of the circle down to the chord. This brings us to theorem 6.4.5. The geometry dictates that the chord positioned closer to the center of the circle is always the longer chord. Conversely, the shorter the chord, the further it is pushed away from the center toward the perimeter, and this length connects right back to the edge. A longer chord will always correspond to a greater minor arc along the perimeter. Whether we are on the outside engineering external tangents using precise 90-degree logic, or on the inside measuring internal chords and arcs, every element of a circle is locked in a rigid, provable system of mathematical proportions.